Here we're going to talk about various ligands in coordination compounds, how they go about binding, and different types of ligands. So we can divide ligands into two different classes. One's classical or a simple donor ligand, and this is more along the lines of what we've discussed. So they're ligands like NH3 or H2O. So these are called amine or aqua ligands. These are the electron pair donors. So again, Lewis bases. And they donate those electrons to that metal center, forming that coordinate covalent chemical bond. And they do form complexes with a bunch of types of Lewis acids, even H+, for example, which we're familiar with things like NH3 or H2O, but also with metal centers that are Lewis acids. So these are classical or simple donor ligands because they really do form bonds with the vast majority of Lewis acids, not just metals specifically. Then we have non-classical ligands, pi bonding or pi acid ligands. And these will take a little bit more, we will talk about more in the future. They're a little bit more challenging to understand why they bond the way they do. So they're ligands like CO, so a carbonyl ligand, benzene, for example, some things like that. They will pretty exclusively form compounds with a transition metal center, not with all Lewis acids. So it makes them more prevalent in coordination chemistry and inorganic chemistry than you will have found in organic chemistry, for example. So this carbonyl ligand, the C triple bond O, is a classic example of this. And it can form with a metal, but you won't see that forming with H+, for example. Like I said, this bonding occurs because of some other properties that are associated with the ligand and the metal, and it will take a little bit more understanding for us to really justify why this is occurring. And it'll take more of an in-depth dive into molecular orbital theory to really justify why this is occurring. So these ligands, these pi acid ligands, they can engage in both sigma and pi bonding with transition metal. And that's part of the reason why we end up observing them bonding to a metal center more exclusively. They can not, they're certainly donating their lone pair of electrons to the metal center with a sigma bonding interaction, but also because of these other like p orbitals, they can utilize bonding that accepts electrons from the metal via a pi bonding interaction, and that will also that essentially is what allows it to undergo binding to a metal center. Again, this is a relatively simplistic view of what's occurring, and we'd have to dive into more details with molecular orbital theory to really justify this sort of interaction. This is the origin of the name, the pi acid. It's because of that pi bonding from that metal center that allows these ligands to undergo bonding. Like I said, it'll be discussed in much more detail later. So anytime we talk more about molecular orbital theory or organometallic chemistry, that's when we talk about these pi acid ligands in a little bit more depth. So we know many ligands are also able to bond to more than one metal at the same time. These are called bridging ligands, and here are some examples of various bridging ligands. And they are fairly common, so we end up seeing a lot of these with coordination complexes. You can have a unidentate bridging ligand, and that's where a single atom bonded to two or more metals. So that's like the chlorido, which is the chlorine-based bridging ligand there. You can also have ligands that having more than one donor atom can behave as bidentate bridging ligands, for example. Over on the right, that's where you get the sulfate or if you deprotonate a carboxylic acid, form a carboxylate. Both of those oxygens can also donate to a metal center, for example. So you can get bridging ligands like that as well. These ligands can be classified structurally by the number of connections they make to the metal atom as well. So a ligand where only one atom is bonded to the metal is called unidentate. And a ligand becomes more bonded to the metal by two or more atoms. It's called bidentate or tridentate, for example. Here are some examples of bidentate ligands in which you form various size rings. So bidentate ligands are very common. You can form a 3-membered ring, 4-membered ring, but 5 and 6-membered rings are more stable, and that's again just a sterics argument. And this is also called chelation. So you could call this a chelate ring, being the size of that ring bonded to the metal center, which here is signified as a capital M. So we have something called the chelate effect or chelation effect. And you can actually have some enhanced stability of a metal complex that's formed with a certain number of dentate ligands versus the unidentate ligands. So if you have bidentate ligands, it's essentially saying that the bidentate ligands are going to coordinate more strongly than the similar unidentate ligands. So if you take a look at this nickel complex, nickel can form a coordination or a complex ion with ammonia there. And so that means the nickel will be octahedrally coordinated, in which it has 6 nitrogens around it. And the lone pair on the nitrogen are being essentially donated towards that nickel, which is that coordinate chemical bond. And that's that Lewis acid, Lewis base adduct that we've been talking about. That will be less stable than the bottom situation where you use ene, which is ethylene diamine, and that can be seen on the right-hand side. That is very similar. You're still going to have 6 nitrogens coordinating to the nickel metal center, but they have an ethane bridge between these nitrogens. So these are actually 3 bidentate ligands. So even though the coordination environment around the nickel is the same, when you have 3 ethylene diamines, those will be much more stable than the 6 ammonias that would be coordinating. So where you're forming those 3 chelate rings, that's formed nearly 10 to the 10th times. That's more than 10 to the 10th times as stable, in which you would just have no ring formed, meaning those just dangling off the sides. So it is very, very preferential for them to form bidentate modes. Part of that is when one of them already attaches. The next one is so much closer that it's very, very, very likely for it to form. And in this case, it's also forming a 5-membered ring, which there's not a lot of sterics involved with that, so that's totally fine. There are some other tridentate ligands that are rigid, so they can only do certain geometries. So some are called obligate planar. So they're forced by pi conjugation to favor being planar. So here's terpyridine, sometimes called terpy, and that is a totally planar complex. So those 3 nitrogens all have lone pairs, so they all can engage in bonding to a metal center, and that's what those arrows are indicating. But they can't just be in any geometry whatsoever. They kind of have to be in one particular geometry. So there's times where these ligands can force a particular geometry, for example. So this is how you could write those. So L is just generically ligand. The lines connecting those the L's on the ligand are just showing that there is some sort of macro structure that is holding those together. So it's showing that it's a tridentate ligand on those bottom examples, for example. But they're not just in any orientation. They're all planar. They're all along the same plane. So you can kind of have those situations occurring as well. So this is kind of a shorthand for how you would draw these. Sometimes people will not draw the entire ligand because the ligands can get fairly complex. So instead they'll use a shorthand like this. There's also flexible tridentate ligands. So diene, so diethylene triamine, for example. And here you have a bunch of different nitrogens that all can bind to a metal center. So here, there's a nitrogen here, and a nitrogen here that all can bind to a metal center. And you still have these two CH2 bridges between them. So it's similar to the ene, but where this right here would be ene, this is diene. So it's just adding one more of these, becoming tridentate. They can form complexes like this. So you can see, since it's flexible, it doesn't have to be along the same plane. It can actually bend and be in these three locations in an octahedral geometry. You have quadradentate ligands. Okay, triene is yet another example of that. So very similar to diene or ene, but we're adding a few more ethane bridges here. And now you have four locations in which you can coordinate to a metal center. There's also some other ones like Schiff base, which is derived from acetylacetone, for example. So this is a scenario in which you can get a quadradentate ligand. There's also tripods. Here's an example of a tripod, right, where you have kind of different, potentially even different atom types. Yeah, tripod is kind of what it sounds like. Then you can also have macrocycles. So instead of just coordinating, instead of having this coordination that's flexible, it's actually totally surrounded. So it's completing a macrocycle, a cycle. And here are some of these macrocycles. They can be planar, for example, things like that. They often will have nitrogens in them, just like so, in which the metal center would be placed in the middle here, for example. That could be a scenario. You also have something called the macrocycle effect, and this is somewhat similar to the chelate effect or chelation effect. And essentially, there is some stability in having a completed macrocycle. If you think about, for example, something that has this example where you still have 4 nitrogens that can coordinate to the metal center, but this is kind of floppy, right? It isn't locked in the position in which you would expect it to coordinate with a metal center like copper, where the macrocycle is already in that particular geometry, so it's actually going to be more stable to invite that copper into the center. So if you were to mix these two together, this macrocycle will actually outcompete this ligand, even though you can see that there are lots of similarities between this ligand and this ligand and this macrocycle. So you can see that with the log K. So that's called the macrocyclic effect. Here are some examples in nature. So with chlorophyll and heme in hemoglobin, where these actually are nitrogen-based macrocycles, and so they can actually form some fairly stable complexes, coordination complexes that have these macrocycles encompassing a metal. Another interesting scenario from nature, coenzyme B12 is actually the only known organometallic compound that exists in nature. And just as what we mean by organometallic compound, so organometallic means that you have a metal bonded to a carbon, so a direct bond between a metal and a carbon. So that's the organo, which is organic, right? Carbon, and metallic, metal. So here you have a metal carbon bond, and that's that cobalt to that carbon of that CH2 that you can see in coenzyme B12. There are many synthetic organometallic compounds, and it's a whole area of inorganic chemistry. But in terms of nature utilizing organometallic compounds, it is not a very common occurrence. You can have higher dentate ligands. So EDTA is probably the best known scenario, and depending on the pH, there are many locations in which it can bind. It has these 4 oxygens certainly, but there's also these 2 nitrogens here that potentially have some ability to bind. There's some other examples like crown ethers as well, and cryptates. You can have cyclic or polycyclic ligands, and crown ethers, for example, are well known for alkali or alkaline earth metals being the metal inside. So crown ethers are named for the ring size and the number of oxygen atoms. So 15 crown 5 is an example of a slightly smaller one. You can also have like 18 crown 6 is a slightly larger one, and one that can have dibenzo on it, for example. So these are other examples of these kind of cyclic multidentate ligands, where you still have the lone pairs on these oxygens that are contributing to the metal center, and that's where you're forming these this sort of coordination. So you have cryptates, bicyclics, sarcophaganates. There's all these interesting terms for different sort of macrocycles or bicyclic species that can totally encompass a metal center, and they have different cavity size that you can vary based on the linkage between them, and it can give you some really interesting chemistry in the sense that it can have high selectivity for particular metals, for example, based on size and charge. And so these are used or are of interest for a lot of different reasons, but especially in terms of that cavity size. So you can certainly put metals in there. These sorts of complexes may be of interest for other sorts of trapping other small molecules inside of those bicycles, for example. Okay. One of the last types of multidentate ligands, you could call it an encapsulating ligand. So this is these actually need to be synthesized around the metal ion, which is actually the template. So you can't really be released from the complex if you are in this situation as a metal, but you'd have to totally break apart this thing in order to get the metal out. So because of this, you can get these complexes that are extremely stable, even in pretty adverse conditions. So these could be useful for a lot of scenarios in which you might be in, let's say, very acidic conditions or elevated temperatures or things like that. So that was a survey of ligands and their various binding modes. Next, we'll be talking about coordination numbers and coordination structures of these coordination compounds.